If we look at the graph of y equals 1 over x, we notice that the function explodes near 0 because 1 over 0 is undefined. So naturally, if we integrate 1 over x from negative infinity to infinity, we get 0? Integrating this function over these bounds is impossible using the fundamental theorem of calculus because 1 over x isn't continuous over these bounds. But what if we tried a contour integral in the complex plane? If we make a nice little contour that jumps over 0 and then circles around in the top half of the complex plane to get back where we started, 1 over z is analytic everywhere inside the area bounded by this contour. So by Cauchy's integral theorem, the integral of 1 over z over this contour will equal 0. Now let's name everything here on this contour integral. We have I1 and I2, which are the parts of this contour that travel across the real line. We have big gamma, which is this counterclockwise circle around the top half of the complex plane, and then we have little gamma, which is this clockwise circle. The idea is, I can say that the big circle of this contour has a radius big R, and the little circle has a radius epsilon. Then, if I take a limit as R goes to infinity and epsilon goes to 0, what I'll be left with is these two segments, which will add up to be our integral from negative infinity to infinity of 1 over x, and then these two circular segments, which we'll deal with. Because little gamma is a semicircle around a pole, we can evaluate it using the fractional residue theorem, which tells us that the integral of little gamma is going to be pi I times the residue of 1 over z at 0, and we know that the residue of 1 over z is just going to be 1 because it's the coefficient of the 1 over z term. So the integral over little gamma will be negative pi I because we're going clockwise. If we were going counterclockwise, it would be pi I, but clockwise makes it negative. The integral over big gamma we can solve by letting z equal r times e to the I theta. So when z is equal to r times e to the I theta, we get that dz is ir e to the I theta d theta. And then when we plug everything in, we get the integral from 0 to pi of ir e to the I theta d theta over r e to the I theta, which just leaves us with pi I. So the integral over big gamma was actually completely independent of the radius big R. Pretty neat. But what this means is that our contour integral, which was equal to 0, is equal to I1 plus I2 plus pi I minus pi I, and those pi I parts just go to 0, leaving us with I1 plus I2. So if we take a limit as R goes to infinity and epsilon goes to 0, we're left with I1 plus I2 being the integral from negative infinity to infinity of 1 over x dx, which we've now shown is equal to 0? Because I've gotten a finite answer for this divergent integral, we tend to call it a principal value. See, if we look back at the graph, you'll notice that the positive divergent part is naturally going to be the same size as the negative divergent part, and so if we summed them together, in a sense we could say that they sum to 0. So though we can't solve this integral using Riemann or Lebesgue integration, we can do it using a contour integral in a sense. So that's pretty cool. Thanks so much for watching, and I hope you have a nice day.